Here is 11.3. It's ellipses. So far, we've covered the first two conic sections, circles and parabolas. So now it's time for ellipses. So what is the ellipse? If you remember the shape, it's like an elongated circle. So I'm going to draw one for you here in just a minute. But first, let me give you the standard form of the equation. The standard form for the ellipse right there, and that might remind you a little bit of the circle. So we see x minus h quantity squared, but that is divided by this number a squared, plus y minus k quantity squared divided by b squared. And an ellipse, it's always equal to 1. So what's going on here? Well, we see the h and the k again. That's kind of the theme of this chapter. And so that's the center of your ellipse, HK. What are the A and the B? Those are kind of like the equivalent to the radius, except A we think of as a horizontal radius, B as the vertical radius. Here's what I mean. So here's the drawing, and we'll label it all. So here's your elongated circle, your ellipse. I've got it going, kind of more wide than tall. So the center, well, right there. And then you think if A is the horizontal radius, then out to the edge here is A, and B, the vertical radius, up straight up to the top is B, and then anywhere in between that distance from the center would be somewhere between the A and the B. Okay. All right, so a big part, what we're going to be doing here, same sort of problems that we've seen with circles and parabolas. We're going to be given an equation and asked to graph it. And sometimes it takes some work to first put it into the standard form, but sometimes they go ahead and give it to us in standard form. Oh, I was getting right to the examples. I want to talk about some applications of the ellipse first, just very, very briefly. So here's what's going on. You might think, what's the relevance of this shape? How is it important? What is it all about? So here are some, just some kind of uses of the ellipse before we get into the examples, which I was about ready to dive into. So here's a couple, and they deal with how the planets orbit. So it turns out all of the planets orbit along an elliptical path. So let's say here, I've got the Earth out here and the Sun. So the Earth travels around the Sun in an ellipse. Sometimes the Earth is a little bit closer to the Sun, and other times it's a little bit further away. Now this is really exaggerated. The orbit of Earth is not nearly this elongated. It's much more circular, but it's not a perfect circle. So some of the planets and comets and things like that, they really have an elongated ellipse. Sometimes a comet will shoot in and come very close to the sun and then get flung out and go really far back away. All the planets are almost perfect circles. They're very close. But the same thing would go for satellites orbiting around Earth. The same would be true of the moon. They all orbit in an ellipse. How about this? What is this? Okay, so this, still think about, maybe Earth going around the sun. So what's going on here? So I've got the path of Earth. So imagine Earth is right here. Okay. And then 30 days later, the Earth is right here. All right, so it took 30 days to go that distance. Of course, it's 1 year to go all the way around. But okay, in 30 days, it moves that far. Think of the area created when you draw lines from the sun. So the sun to that distance and the sun to that position. Think of that area. So it turns out any 30-day period will mark off the same area. But as you get closer to the sun, it looks different. So let's say, a few months later, Earth is right here. 30 days later, Earth is right here. Well, it's much closer to the sun, but still, if you draw those lines and think about that area, those areas are equal if it took the same amount of time. I don't think my drawing is quite accurate, I, uh, but I think you get the idea. So that's pretty awesome. That was discovered back in the 1600s by a guy named Kepler, who was studying the orbits of planets and things, and he used the ellipse. Okay, I've got one more application for you. I can't not tell you about this one. There are lots of applications of conic sections, and the ellipse is no exception. This is pretty cool. Okay, so imagine someone is standing on the earth and they throw an object and the object travels up into the air and then back down and hits the earth some point later. So we studied that sort of thing back in chapter 9 when we studied quadratics, when we studied parabolas actually for the first time. If you throw an object up, we said it travels along the path of a parabola. Okay, and the peak, the maximum height is where your vertex is, right? But here's the thing. We've drawn the earth as flat. If the earth is flat, you get a parabola. But the earth isn't really flat. The earth is curved. So think about this. Take that same person and he throws the object, and he really has an arm on him. So he throws the object so high up that by the time it comes down, it's like gone over the horizon, right? So to him, the horizon is like out here somewhere, right? That's as far as he can see. And then it starts to curve back the other way. So he's throwing it so far, it actually goes over the horizon to him. Well, is that a parabola? No, because we've got this curved earth. If the earth is a curved world, that shape is actually just the very top of an ellipse. If you imagine the center of the earth, and we'll just put it right here. I don't think this is near far enough away, but we'll just think about it like that. So if this was to continue traveling and then fall down through the earth, it would act just like a planet in orbit. So it would come down, it would go around the center of the earth, and then it would eventually come back to where he threw it. And you would get this ellipse. So truth is, when you throw an object and it comes back down to the ground, it's very, very close to a parabola, but it's curved just a little bit inwards. It's actually the very, 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 very top of a very skinny and long ellipse. Okay, I had to talk about that. It's just too cool. Now we can get to the examples. Okay. So we'll do an easy one and a hard one. I think that's a good way to go about it. Got my graph paper ready here. Let's check this out. So this one is in the standard form already. X minus 1 squared over 16 plus y minus 3 squared over 9 equals 1. If you remember, the standard form, it's this. Okay. So if we are being asked to graph, then we'll need to identify the h, the k, the a, and the b. Let's start with the h and the k. Well, I see in standard form it's x minus h. Here I've got x minus 1. So h must be 1. And in the same way, the k must be 3. So the center of this ellipse is 1, 3. Okay, well, at the same time, I'm showing you the values of a and b. If this, what I'm looking at, is a squared, then what must a have been? If 16 is a squared, a must have been 4, right? And if 9 is b squared, then b must be 3, so that when I square it, I get the 9. Okay, perfect. I've got the center. I've got the horizontal radius, the vertical radius. I'm going to pull this off the screen and grab my graph paper. Looks like I need to create an XY plane on this first with my Sharpie. Okay. Maybe I'll turn it sideways even. That'll work well. So the center is at 1, 3. So 1, 3 right there. And then I'm going to count horizontally the distance A. So that's 4. 1, 2, 3, 4. And back this way. 1, 2, 3, 4. My horizontal radius. And my vertical radius in both directions. 1, 2, 3. 1, 2, 3. And then I'm going to create that ellipse in a very similar way to we do the circle. Try and connect all of those pieces. Make it nice and rounded. People tend to, angle these too far inward, and it looks like a, more like a diamond or something. Keep those nice and rounded, nice and smooth. There's the graph of this one. Okay, let's continue with a more difficult example. Oh, actually, I've got 3 examples for ellipses, not just 2. So we're getting progressively harder. All right. How about this? 3x squared plus 4y squared equals 144. Okay, well, before I can even attempt to graph, I've got to get it into the standard form. So how are we going to do that? Well, this one's not too far away from it. We definitely need some work because it certainly doesn't look like this, but it's not nearly as far off as what we're going to see later. Here's the key. I see 144 there, but we've got a 1 in the standard form. So the first goal is to make that a 1. Now, what's the best way to change the 144 into a 1? Let's divide it by itself. Let's divide it by 144. Of course, if we divide the right side by 144, we have to do the same thing to the left side. So we're going to divide both sides by 144. And then we're going to, just sort of play around with the left side, and eventually we're going to get it to look like this after a couple more steps. Okay, so we're dividing both sides by 144. Well, if you look on the left, I've got the 2 parts in the numerator. I can divide them each separately by 144. So I can say 36x squared over 144 plus 4y squared over 144. Think of it as reverse common denominator, right? Normally we go from this step to here to combine them. Well, we could go backwards if we wanted. They're all equal. And at this point, we can say the right side just equals 1. And we are 1 step away. All we need to do is reduce those numbers. So 36 over 144, 4 over 144. Now the best way to do that is to actually do it backwards from what it looks like. So where we see 36 over 144, do 144 divided by 36. And whatever the result is will be the denominator. And same thing here, do 144 divided by 4. And the result will just be the denominator since we flipped it. Well, if you do that, I think I can shift everything up. Over here, if you divide there, you'll get 4. So 4 is the denominator. Here, if you reduce, you'll get 36. There. And now we have it. We have the standard form. Actually, a very simple standard form because you don't see all the h and the k. We'll talk about that in a moment. Okay. Also, you might notice the 36 and the 4 appeared there and there. That did happen. This 36, when we were all done, came to this denominator and this 4 came to this denominator. You see that all the time in these questions. Don't ever assume it's going to happen, because, you know, that one time you assume, then it's probably going to be the time when it doesn't happen. But, you know, don't be surprised when it does happen, I guess is what I'll say. All right. So let's identify HK, A, and B from this standard form. What are H and K? Well, they're both 0. It's like we're saying x minus 0 squared would just be x squared, right? And it's the same thing with the k. So our center is 0, 0. What's under the x squared? We think of that as a squared, so a must equal 2. This is b squared, so b must equal 6. And that right there is the information that we need to graph. Let me pull these things out of the way. Grab some more graph paper. Again, I need an XY plane. Should have done this ahead of time. Okay, I'm going to keep it oriented this way. So there's the center, and then I'll move 2 horizontally, and I'll move 6 vertically. And I've got this very tall, thin ellipse. I'm going to do something like that. Okay, I think that's all right. I'm not going to grade you on your artistic skills, but please try to make it curved. Don't draw, you know, perfectly straight lines there. There is a curvature to it to connect those points. Okay, let's stop this video here. I got one more example coming up.